So in this hour, we'll talk about another routing algorithm, routing protocol called distance vector. Okay, the concept of distance vector is similar to link state, but some different, of course. Bellman-Ford, two different experts, they built this distance vector algorithm. The basic concept of distance vector is recursive or called dynamic programming. So here's the Bellman-Ford equation. Okay, think about one thing. We have to evaluate one value, which is dxy. That means the distance between a node x and node y. Okay, so and of course there are a lot of different other nodes, which, for example, v1, v2, v3, v4, and so on. There are a lot of different nodes which is directly connected to x, right? That is very easy to understand, right? So basically, each link has their own cost: cx v1, cx v2, cx v3, cx v4, and so on and so forth, right? So that is. The next question is, although those v1, v2, v3, v4, those nodes directly connected to x, but how do they find a path to the actual destination y? So the answer is we don't know. So I draw dot line right here. Basically, we don't know. We don't know how v1 connected to y directly, or they can find a path to y. We don't know. But there's one important thing that even if we don't know how v1, v2, v3, v4 connected to y, but actually I can simply just write it down. So the distance between v1 and y, it should be distance between v1 and y, right? The other one's v2 y, v3 y, v4 y, right? And for x, it knows all the blue color cost, right? Because it directly connected to v. But for v1, v2, v3, v4, the dv1, dv2, dv3, dv4, y, x does not know such value, but the x can ask v1, v2, v3, v4 to advertise a number of dv1, dv2, dv1y, dv2y, dv3y, dv4y. Although x does not know the actual value and does not know how v1 connected to y, but it can ask v1 to advertise a number of dv1y to x. So in this case, dxy can be represented as cx v1 plus dv1y, cx v2, dv2y, cx v3, dv3y, and so on and so forth, so on and so forth. No matter how, after x get all the dv1y, dv2y, dv3y, all those values, x can calculate dxy. Simply just choose the smallest value in this set, and then that is dxy. All right, so that is a very simple way. But the next question should be like this: how v1 knows dv1 of y. But it's still the same. It's still another question, right? dv1 y. It should be some values, okay? cv1, for example, next for u1, cv1, u2, cv1, u3, so on and so forth. And just again, try to find another u1, u2, u3, which can connect it to y. And you can, again, write exactly the same equation. Right here, the purple one, to evaluate the value of dv1y. So it's something like a recursive call. Okay, we call it a dynamic programming problem. Okay, the answer is recursively use the other call, the distance function, and so on and so forth. And eventually, there should be some node which is directly connected to y. Right? Eventually, there should be some nodes which are connected to y, so they can evaluate the wy, for example, dwy directly, because it is directly for example, some w is directly connected to y, so cwy is exactly equals to dwy, right? If w is directly connected to y. So basically, we can use this kind of information passing to ask all the neighbors, all your neighbors, to evaluate the value to your destination, and your neighbors will ask their neighbors to evaluate the path, and so on and so forth, so on and so forth, so on and so forth. Okay, so I think the concept is quite simple, but the calculation is not that simple. Okay, let's take a look at this one. Okay, so we would like to evaluate duz, right? duz. So first, you have to know what is the neighbor of u, which is v, x, and w, right? Because v, x, w are directly connected to u, and we simply just write down. We would like to ask v, x, and y, how do they evaluate the distance between v, x, w to z, respectively. Okay, and as u, right? We are u, right? As u, we know the cost of those links because they are directly connected to myself, to u. So CUV is 2, CUX is 1, CUW is 5. I can measure the cost by myself, u, as a u. And DVX, DVZ, DXZ, DYZ, we simply just ask those nodes to reply, to estimate DVZ, DXZ, DYZ. And they will tell me, okay, the V will tell you, say, DVZ is 5. X will tell you DXZ is 3. W will tell you DWZ is 3. And then we can simply just do the math and say, okay, then I know. If you would like to go to Z, and it should pass the packet, forward the packet to X, because X should have a minimum path. Right, so that is the idea of Bellman-Ford, or what we call distance vector algorithm. Okay, we skip this one, we'll come back later. Okay, so as I said, the algorithm is not that complex, but the calculation itself is a little bit complex. Okay, so let's take a look at the right hand side. This very simple topology. Okay, we have x, y, z and the corresponding links. So right here we have x, y, z, 3 individual router, and each router has to calculate its forwarding table, right? So this part is the forwarding table of x at time 0. So at the very first beginning, okay, before x and y, z exchange messages between their neighbors, okay, x, right, x only knows, okay, CXY is 2, CXZ is 7 because x has direct connection to y and z. And of course, CXX is 0, right? CXX is 0. It's the same. At the same time, y knows its cost to its neighbors are 2, 0, 1, and z knows its cost to neighbors should be 7, 1, 0. So that is time 0. That is time 0. Okay? At time 1, at t1, okay? Because y and z, they are connected to x, so they can send messages to their neighbor x. So y and z will broadcast its current information 201 and 710 to x. So x will simply just write down 201 and 710 in its table, in this distance vector table. Okay, but after x receive the information from y and z, but the information is based on t0, right? Okay, x should update its distance vector. Okay, again, xx should be always 0, right? So let's take a look at this one. X, y. So this number should be the distance between x and y, right? So let's again, dxy, we can simply write, okay, x, if x go to y first, or if x go to z first, and we then evaluate dyy and dyz, and that should be the Bellman-Ford equation, right? Okay, again, okay, try to do it again. Okay, we start from x, and we want to know the destination should be y, so x is right here, x is right here, y is right here, and y is right here. And we can pass through different hosts, different router, right? The router is y, one of the router is y, the other router is x. We have to evaluate 2 different routes. Okay, and again, take a look at this one. CXY, this should be 2, because it's CXY, it should be 2. It's right here. We have some old information, okay? CXZ should be 7, CXZ should be 7, because at the first beginning of T1, okay, we have the information of T0, okay? And let's take a look at the DYY and DZY. That is advertised by y and z at time 0, but we got the number at time T1. So DYY should be always 0, but DZY is advertised by z. I think this should be right here. It's advertised by z. So the minimum number should be 2. It does not changes. Okay, it does not changes. However, let's take a look at another one, which is the red one. This number. This number should be dxz. That means I would like to go from x and ends with z. And let's take a look at this one, okay? If x go to z through y, and if x go to z through z. And again, we can simply get this value 2 and 7 from the distance vector given this distance vector by x, because x already known it is 2 and 7. But we can get the information of dyz and dzz from the advertisement by y and z at after t0. So it is 1 and 0. And the answer is 3. So that means x can go to z through y, which is much shorter than x go to z directly at t0. So at t1, we update this value because we got the information from y and z at before t1. We got the information of t0 from y and z before t1. So at t1, we can calculate the new distance vector for x. Originally, it is 0, 2, and 7. Now it's 0, 2, and 3. Okay? But still, you have to think about one thing. That is just one of the table. You have to think about one thing. Again, x will advertise the information it gathered at t0, and z will advertisement its information gathered at t0, which is 0, 2, 7, and 7, 1, 0 to y. So y have to calculate, have to update its distance vector, okay? And again, x will advertise its value, y will advertise its value to z, and z will calculate its new, it will update its distance vector at time t1. So we simply just don't cut. We simply just did not calculate right here. Okay. But in this case, we can anticipate that this value, the new updated distance vector of z and the new distance vector of y should be a little different from the value at t0, because we can update some path, right? Some path right here. And again, the next part is at t2. Again, they have to again update value in this way. I think it's right again. So after several different iterations, x and y will exchange messages, exchange information to all the other to its neighbors, to all their neighbors. Okay, and after that, the entire distance vector at x and y and z will stabilized. Okay, here is the result. Okay, I think one of value is updated right here, the other is right here, right? After they do the blue update, okay, dxz will be updated. Okay, after they exchange message right here, this value dzx will be updated. Okay, and again, right here, after the red update, dzx will be updated as well. Oh, sorry. I think it should be so now this one. Let's think about okay, I think that is only these two values, the blue one and the green one, will be updated by the Bellman-Ford equation. But after that, again, because x change its value, so it will be updated right here. The z changes value right here, so it will be updated right here. It will be updated right here, and it will be updated right here. The pink one, the red one, they are updated simply just share information. But the green one and the blue one, they are updated by Bellman-Ford equation. Okay, I think that is. Okay, that is. The pink one is simply just x update its value, so it share with y and z. Z share its value with x and y, but they do not. After Bellman-Ford equation, all the other values are still the same. Okay. Okay, I try to calculate this table by yourself. Okay, but you have to understand that there are several different timestamps. Okay, so let's go back to here. So basically, key idea is this equation. Okay, you have to try to calculate this value by using this equation. Okay, so and again, we do a lot for each node. Okay, they simply just wait for wait for advertisement and could calculate the rest of the value by using Bellman-Ford equation. And if you update your value, you simply just send the updated value to your neighbors again, and so on and so forth, so on and so forth. Okay, all the update are asynchronous. That's because when you send information at T1, basically all those information are from T0. So everyone, when they calculate the value of T1, there may be some new values are updated, but those updated value will be transferred before T2. So after T2, they will do the calculation again. So we say they are iterative, and those nodes receive information asynchronously. Okay, and it's a distributed information because everyone just simply do calculation and send information to its neighbors, and it can be self-stopping because after your table is stabilized, when your table does not change, okay, and then that's it, you can stop the algorithm. Okay, and by using the distance vector right here, you can calculate your forwarding table. Okay, so that is distance vector, but it has two other problems, two other properties. So I'd like to talk about. The first one is this one: good news travels fast. Okay, think about one the graph at the right hand side. If the cost CXY, okay, originally it is 4, but now it decreased to 1. That maybe because you have a new link, you have a faster link that is less congested, any reason, but it decreased. Okay, so think about one thing. At time 0, Y detect link cost change, right? So it update Y's distance factor, and it will inform its neighbors. Right? Will inform its neighbors. Okay. At T1, Z receives such kind of update from Y. Okay. So take a look at this Z. Okay. DZX. Okay. So by Bellman-Ford equation, starting from Z ends with X, and if it goes past X or if it past Y, so C at Z, okay, at Z, CZX it should be 50, CZY it should be 1, right? DXX it should be 0 because it is same node, right? But the question is, what is the current DYX? As we mentioned before, Y should advertise its distance vector to its neighbor, which is z and x, right? So it was 4, but currently it is 1 right now. So the answer should be 2, right? It was 5, but currently it is 2. Z can go to x through y by only use cost 2 units of something. Okay, so it only takes 2 iterations for y to advertise such kind of information to its neighbor, and its neighbor will directly update its distance vector. So we say good news travels fast, and then at time after time t2, all the distance vector become stabilized. Okay, so they will stop updating their distance vector. Okay, but I think the problem is right here. Bad news travels slow. Okay, again, think about this example. dyx, okay, dyx changes from 4 to 60. Okay, so we simply just look at the equation right here. Okay, originally let's take originally dzx should be 5, right? Originally it should be 5. Okay, so let's take a look at the equation right here. I would like to calculate from distance from y to z, okay, through x or through z. cyx, okay, cyx, it was 4, right? It was 4, and dxx it should be 0. cyz it should be 1. dzx, okay, dzx was 5, right? Because originally dzx, z should forward the packet to y and y goes to x, so the originally it should be 5, right? But at z only knows it takes 5 units of cost from z to x, right? So it advertised dzx to all the other its neighbors. So y will receive such kind of information that if you want to transfer a packet from z to x, and the cost is 5, because this information was broadcast, dzx was broadcast by z to all its neighbors, including y and x. So after y sends the link cost from 4 to 60, and y will try to seek another route to x, because currently cyx becomes 60. Okay, but actually when z do such kind of advertisement dzx to y, actually y does not know how z choose a path to y. Maybe there is another route and the cost is 5, because y does not know how z goes to x. Y only had been advertised by z, and z said I can go to x with 5 cost of 5, but y does not know how z goes to x. Okay, So after that, when y trying to update its distance vector, okay, the upper one is 60, right? But the lower one is still 1 plus 5, which means 6. So y knows that, okay, the current dyx is 1 plus 5. Although I don't know how z goes to x, but z advertised that it can go to x with only 5 cost of 5. So y will update its distance vector to 6. But after y calculate this new value to 6, and then we change to z. Z knows when it tries to send packet to x, it should go through y. Z knows that, okay? Z knows that. But currently this value becomes 6. So z will update its dzx from 5 to 1 plus from 1. It was 1 plus 4, right? It was 1 plus 4. But currently it will be 1 plus 6. And so on and so forth, so on and so forth. Right? Right. So if you have time, take a look at your textbook, and it will tell you how this number will grow from 6 to 7 to 8 to 9 to blah 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 blah. Okay, that is at z, that is at y. Okay, at z it was original 1 plus 4, but at y the next iteration will be 1 plus 5, and at z it will be 1 plus 6, and at y it will be next round that will be 1 plus 7, and so on and so forth, so on and so forth, until 44 iterations. Okay, the number will be larger than 50. The number will be larger than 60. So y and z finally they figure out, okay, they should take a new route from y to x through z. The answer will be 51, which is much better than yx. So the update procedure will be very complex. Okay, first y will update and z will update, y will update, z will update, and so on, so on. So bad news travels slow. That is one of the shortcomings of distance vector. But eventually it will be the correct value, but it takes many different many iterations. If you want to know the exact description of this 44 iteration, you can take a look at the textbook. Okay. So the next one, the comparison of link state and distance vector. Okay, the message complexity, we have talked about it before. If we have n routers, link state need to broadcast all the information to all the other nodes, so it takes a big O n squared to send all the message out. But for distance vector, as you know, it really depends on the current situation of link cost and their topology. So we don't have a value of the message complexity. We simply just exchange message between these neighbors. Okay, it converges sometime. Okay, the speed of converge. Okay, link state takes big O n squared to calculate all the values, but it also takes n squared message to exchange message before. But for distance vector, again, it may have routing loops. It comes to infinity problem, so it does not have a precise complexity number. Okay, the robustness. Okay, link state only need to calculate its own link state after it receives all the information. But of course, some nodes may cheat, may broadcast the wrong information, so that the result will not be correct. And for distance vector, because we have Bellman-4 equation, so if some router cheat, okay, they say, okay, there's one example. I have a really low cost path to anywhere, and all the routers will believe, okay, that is for example D cheat anyway. Okay, so the cheater will become a sink because all the routers will believe, okay, the cheater will have a very short, very low cost path to anywhere. So all the packet will be forwarded to the cheater router, like the cheating router. But of course, it is very dangerous to broadcast such kind of information. So I think most of the routing algorithms and routers, they will use encrypt message and use authenticate message to communicate with each other, so that hackers or attackers will not broadcast the wrong routing information to all the other routers. Okay, so that is distance vector, and we will talk about two oversimplified routing protocol. Okay, one is OSPF, the other is BGP. So let's take a look at this one. Okay, when we think about what kind of routing protocols should be used in internet, we think about that the scalability and the administration. Because we have billions of destinations, we have even I think tens or millions of routers in the internet. So it is very difficult for router to communicate with each other, because the message exchange overhead is very large. So it would be better to have some mechanism to help those routers to organize with each other, or to organize under some administration. So we have to introduce a new concept called autonomous system, AS, or as known as domain. Okay, we aggregate routers into regions known as AS, autonomous system. Okay, so we first take a look at this graph. Okay, so right here we have three autonomous systems. Okay, S1, S2, and S3, and in each AS there are multiple routers in a single AS. Okay, and usually in one single AS, all those routers are under the same administration. For example, like NCCU campus. NCCU campus is a AS as well, and all the routers are under control by the computer center of NCCU. So we have a lot of routers in a AS, and maybe AS2 is another maybe another university nearby, something like that. And of course, all these routers are interconnected. So routers in AS1 are connected, and there are some links, there are some edges connect S1, S2, and S1, S3. Okay, so we call, when we do routing, if this packet is routed within an AS, it is inter-AS routing. If a packet is routed among different AS, that is what we call intra-AS routing. And all of these routing there could be different routing protocols to deal with intra-S routing and inter-S routing, but all those information will then become a rule in forwarding table. So basically, routers only need to check its forwarding table to forward packets, no matter the packet is the rule is calculated by intra-S routing protocol or inter-S routing protocol. Okay. So routing among the same S is called intra-S. Routing among S is called inter-S. Okay. Intra-S. Okay. All routers in AS must run same intra-protocol domain because most of the intra-S routers are under same control. For example, under the computer center in NCCU, so they can run the same intra-S routing protocol to determine how to route packet within an S. Okay, router in different S can run different intra-domain routing protocols because it's intra-S. Okay, how intra-S protocol is used is depend on different S administration. Okay, and the right hand side, the gateway perform inter-domain routing. Okay, let's take a look at this figure. Okay, so if a packet arrives at 1A in S1, okay, it has to check the forwarding table, right? But the forwarding table is calculated by intra-S protocol, right? So AS A1, 1A, 1B, 1C, 1D, they know how to forward this packet if this destination is in the S1 as well. But if the destination IP address is outside at AS1, okay, it has to forward the packet to 1B or 1C depending on the inter-S protocol result. Okay, as we mentioned before, S2, okay, that is another S. Okay, like Bellman Ford, it will advertise where it can go and how long and what is the cost. Okay, so depending on the destination address, B1B and 1C, okay, will receive the packet and forward the packet to S2 or to S3 through 1C. Okay, but how do we know this packet should go to 1B or 1C? Is rely on the calculation result of inter-AS routing protocol. Okay, that's quite straightforward. Okay, and again, let's take a look at this one. There are some commonly used intra-AS routing protocol, but actually, we simply just use OSPF. Okay, Open Shortest Path First, OSPF routing algorithm. It is a de facto standard. So it is a link state routing protocol, so it uses shortest path. So it should contain less routers. It should have a global view, as we mentioned before in Dijkstra's algorithm, right? So let's take a look at OSPF. Okay, it is a classic link state fashion routing protocol. Okay, open means it is open to the public, so every router can implement this routing protocol. Okay, as we mentioned before, for Dijkstra algorithm, for the link state routing algorithm, all the node in the topology should get all the information, right? So each router flood OSPF link state advertisement via directly over IP to all the other nodes in entire AS. So that is it's aligned with Dijkstra's algorithm, Dijkstra's design. Everyone in the AS should know all the information of all the other routers in the same AS. Okay, the information is broadcasted, is flooded by using IP protocol. It's not UDP, not TCP. It is simply just some information attached at the end of IP header. Okay, so all the other nodes should get all this information, not only just neighbors. Okay, and again, as we mentioned before, you can use different metrics as the link cost. okay, bandwidth or delay or congested level, okay. Again, each router has 4 topology, okay. They use Dijkstra's algorithm to compute the forwarding table. This one, as we mentioned, because those information are very critical, so you have to send this message with authenticated way. But we simply just know that. OSPF broadcasts a link state periodically, okay? According to the specification, at least once every 13 minutes. Okay, so I think the most important figure is this one for OSPF. Okay, in this chapter we will not talk about the OSPF format, OSPF protocol, OSPF, how OSPF exchange messages. No, we don't talk about this in our textbook, in our slide. We simply just introduce what is the concept of OSPF. Okay, and currently we call it 2-level hierarchy. Okay, so think about that as our campus network. Okay, so this part is for example the east side of our campus. That is the department or the centers on the hill. Okay, so the other part is the department or the organization in the campus, which is at the west part, for example. Okay, we call it different area. Different area. So different area. Okay, they connected. Their routers connected with each other within the area. Okay, so they run. Okay, they flood link state information in this area only and compute the routing within the area by using Dijkstra's routing algorithm, link state. So in this case, only small amount of router will be included in a small area, okay? And they can run Dijkstra's algorithm. So they can share global view within this area. That is quite straightforward, right? That makes sense because only a small part of routers will involve Dijkstra's routing algorithm. Okay, but there's always some routers. They are border routers. That means if any packet will need to be forwarded to the outside of the area, and the default route will be this border router, and the border router will be connected to other routers. Okay, as it mentioned right here, they will be connected as backbone. Okay, so those border routers and the backbone will collaboratively forward packet with among those areas. And again, there will be a very special role right here. It's called boundary router. So as you can see that this specific OSPF hierarchy, they should be under same AS. So AS can be divided into different areas, and those areas will be connected through the backbone. And there should be one or more boundary routers that can connect it to another S, and so on and so forth. Okay, that is the hierarchy structure of OSPF. Usually it has 2 levels. One is area, the other is backbone. Okay, we have some special characters right here, border routers and boundary routers. And boundary routers will be connected to some other autonomous system S. So that is how networks are interconnected. Okay. So that is OSPF. Okay. The other protocol is BGP, but we will simply just introduce some very simple concept right here next hour. Okay. So we stop right here.